Okay.
Thank you. Gianfranco is always behind the scene and helping a lot.
Guido, do you tell us when we start?
I think Francesco, maybe you can start in a couple of minutes.
Okay.
Another 2 minutes. And then.
Sì.
Okay.
You know that there is a pool of volunteers who are hardly working to manage the lobby, which is not very easy. Francesco, I think you can start now. Thank you.
Okay, thanks, Guido. So, welcome everybody. So this is the opening session, the welcome ceremony of DRCN 2021. My name is Francesco Musumeci. For those of you who don't know me, I am the Technical Program Committee co-chair in this for this conference, and I am also assistant professor at Politecnico di Milano. Today, in this welcome ceremony, we will have few speech. We will have first a welcome message from the General Chair, Professor Guido Maier. Then we will have a message from the Steering Committee Chair, Prosper Chemouille. Then we will have a message from the Department Chair of Dipartimento di Elettronica, Informazione e Bioingegneria, Professor Stefano Tubero. And then I will give an overview of the program, of the content of this conference, highlighting the spotlight events and also technical sessions after these three messages. So first of all, I leave the floor to Guido for his message. Guido, please.
Thank you very much, Francesco, for the introduction, and welcome all attendees, speakers, and invited speakers to this conference. We are starting DRCN 2021, which is the 17th edition of DRCN, International Conference on the Design of Reliable Communication Networks. Actually, the conference started yesterday with the first events, and it will finish on Thursday, 22nd. The conference is technically co-sponsored by IEEE Communication Society, and this is the second time the conference is hosted by Politecnico di Milano in Milan. And this is quite unusual since in principle DRCN moves every year in a different venue, but it was decided by the steering committee, which I thank a lot. Since last year we had the same situation, unfortunately, as this time. So all the conference in DRCN 2020 was played online, and we unfortunately have also to play online DRCN 2021 because the situation is improving, hopefully, but not yet enough to allow international traveling. So this is, of course, something that is not very enjoyable. We would have very much preferred to have all of you here visiting Milan and meeting in person, but this is unfortunately the reality. But we hope that despite the situation, with the program that we have prepared and we are offering to you, we will try to compensate this so that DRCN, as its tradition, its long tradition, can be a venue for a meeting of different people involved in different areas, confronting each other and technically improving and growing, especially for young attendees. For this year, the registrations of students were practically free for everybody. So we hope that, especially in their case, they will take home some message, interesting message, and new expertise. So basically, this is the message that I would like to send to all the participants and the speakers, together with my general co-chair, Professor Kohei Shiomoto of Tokyo City University of Japan, who is connected, and I would like to thank him for the support. That's all from my side, so I leave the mic to Prosper, who will say some words from the steering committee. Thank you. Prosper, you are muted.
Yes, I was muted. I didn't want to disturb you, Guido. Good morning, good afternoon, good evening, everyone. It's my pleasure to be here in this opening of DRCN 2021. For those who don't know me, I'm Prosper Chemoy. I'm affiliated today in CLAM, an engineering school in Paris, France. But I'm retired from Orange Labs as a French service provider. I was in the lab for almost 40 years, and I was a director on future networking for many years. And coming back to DRCN, as it was said, this is the 17th edition, and it was created in 1988 in Belgium, and we went 3 times already in Italy. First one was the beautiful island of Ischia, and then twice now in Milano. DRCN was mainly devoted to reliability, availability, and survivability. It was triggered by a lot of European operators at that time, because many conferences were pushed by operators, and reliability was a key issue, mainly from transmission networks. So it evolved a long time, and today reliability is addressing, as a whole, dependability is addressing a lot of techniques, a lot of technology, a lot of networking aspects. This is why the DRCN is still living. I will not go any further. The only thing I can say that we will break the curse on Milano, and I can say today that next year it won't be held in Milano to release and to relieve the team in Politecnico di Milano. I think that they did a great job all the two consecutive years, and hopefully we get back to normal. And I wish that next we'll come back to Milan again. But in the meantime, we have to go through the technical program of the conference, which is very relevant and very informative and very in addressing really hot topics. So this is I give back the floor to Francesco. Thank you.
Thanks, Prosper. So I forward the floor to Professor Stefano Tubaro for his message. Stefano, please. He is the chair of the Dipartimento di Elettronica Informazione in Bioingegneria in Politecnico di Milano. So please, Stefano.
Hi, Francesco. Thank you. Good morning to all of you. In Italy now it is morning. In other part of the world will be afternoon or even night. But in any case, from Milano, good morning to all of you. As Francesco said, I am Stefano Tubaro and I am the chair of the Department of Electronics, Information and Bioengineering of the Politecnico di Milano. On behalf of the entire department, I welcome you to the 2021 edition of the International Conference on Design of Reliable Communication Network. The COVID pandemic has forced us to use in a massive way the digital communication and collaboration technologies. I think that we all experienced how important reliable networks are to allow that our activities can continue also during this emergency. And consequently, the topics addressed in this conference are extremely topical in this moment. When Guido, some months ago, asked me to say some word during the open ceremony, I accepted enthusiastically. It is a pleasure and an honor for our department to host for 2 consecutive years this international conference. It means that our support services are effective, but obviously the credit mainly goes to Guido, that he is a great event organizer. I do not want to subtract time to the technical part of the conference, but just a few words about the department, our department, and the Politecnico di Milano. The Politecnico is the largest technical university in Italy, with study programs on engineering, architecture, and design, and it is organized in 12 departments. The Department of Electronics, Information and Bioengineering is among them the largest one, with about 240 faculty members. Considering the technical and administrative staff, PhD students, and research assistants, we are near 800 people. The research activities at our department are organized in 6 main areas: automation and control, bioengineering, computer science, electronics, electrical engineering, and telecommunication. Francesco, Guido, me, and the other colleagues present today, we are all belong to these last research areas. You can find more information on our department at the link indicated in the slide that Guido probably is showing now. As in 2020, the COVID emergency has imposed to organize the conference with an online format. But I sincerely hope that in the near future, probably next year, you will have the opportunity to visit in person our department, the Politecnico, and Milano in general. The technical program is extremely interesting, and for sure you will have 3 exciting and fruitful days. I leave now the floor to Francesco and Guido to continuing this opening section.
Thank you very much, Stefano, for your message. and also for your participation to this welcome ceremony, and for informing all the people about our life, our context in DABE and in our department and in Politecnico in general. So now I think we can go a bit deeper into the overview of the technical content that we will have during these days. But before going there, I would like to say a few words of thankfulness to the entire technical program committee chairs staff. So besides me, Francesco Musumeci, there are Jason Zhu from University of Texas at Dallas, Yongli Zhao from Beijing University of Post and Telecommunication in China, and also Giacomo Verticale from Politecnico di Milano here in Italy. I want to thank all of them for the great coordination that we had in managing the technical program, the papers, the reviews, and so on. So I think it was a very nice experience also from my side. So thanks to all of them. Going to the content, to the technical content of the program, as you know, we already had some great events yesterday, and so I take this opportunity to thank all the speakers of yesterday and also the chairs, the organizers of the events that we had yesterday, in particular for the tutorials, the tutorial chair Prosper Shemuiwicz, who organized those events, and the tutorial speakers Eiji Oki from Kyoto University in Japan and Michel Nogueira from Federal University of Minas Gerais from Brazil. And also thanks to the workshop chairs of the first workshop that we had yesterday, Guido Maier, also Marcello Forti from ADVA, and Davide Botto from Highway. I hope you enjoyed the events. In case you didn't, in case you couldn't participate to the events, I take also this opportunity to remind that all the recordings will be available for all the attendees. So also those of yesterday, and this is also applicable for the upcoming events of today and the following days. So today we will start with the technical sessions, and also now I want to highlight the spotlight events. For example, today we will have the first keynote speech from Professor Jafar El Mirghani from University of Leeds in the UK. He is gonna talk about energy efficiency everywhere, cloud, fog, virtualization, and RAN and IoT. And then we will have today 3 technical sessions. Instead, tomorrow, Wednesday, April 21st, we will have in particular 2 more keynote speeches. The first one will be from Masakatsu Fujiwara, who is the head of communication, traffic, and service quality project in NTT Network Technology Labs in Japan. And the second one will be in the afternoon, the Italian afternoon, and it will be given by Gino Masini, who is a principal researcher for standardization at Ericsson in Sweden. And also tomorrow we will have another spotlight event, which is the industrial panel titled Open Solutions for the Next Generation Telecom Infrastructure. I thank the panel chair with Giorgio Parladori from SM Optics in Italy, and also the panelists that will take part to the event, Vittorio Curri from Politecnico di Torino, Andrea Campanella from Open Networking Foundation, Aki Mautenriet from ADVA, Germano Gasparini from SM Optics, Juan Pedro Fernandez Palacios Jimenez from Telefonica, and Christian Jacquenet from Orange, France. The following day, Thursday, we will have 2 more workshops. The first one is in the Italian morning, which is the workshop called Women in Engineering, and the topic which will be addressed in that workshop is the road towards a more diverse post-COVID era, challenges and opportunities. I thank also in this case the chairs of this workshop, Diana Cassioli, who is IEEE Italy section chair of the work group of women in engineering, and also Ligia Moreira Zorello from Politecnico di Milano. The last workshop that we will have in the conference is workshop number 3, whose topic is Beyond SDN, Programmable Data Plane, Abstractions, Architectures and Application. I thank also the chairs of this workshop, Salvatore Pontarelli from University of Rome La Sapienza and Jari Nurmi from Tampere University in Finland. Last, of course, but not least, the core of the DRCN 2021 conference, which consists of the technical sessions. We will have between today and tomorrow 5 different technical sessions. Despite the difficulties in the organizations of papers into sessions according to topics, since we have to somehow, manage the time of the day for the different authors coming from the different parts of the world, we in any case managed somehow to group papers by topic. So we will have 5 sessions. The first one is about resilience modeling and algorithms. Then the second one is about SDN, software defined networking. The third session is about optical networks and telemetry. Fourth session is about 5G, and the fifth session is about wireless networks and security. Besides the technical sessions, for the first time in DRCN, we will have 2 particular events, I would say. The first one is the Gather Town session, which will give us the opportunity to participate in an immersive online user experience, since we will have a platform, which is indeed this Gather Town platform, through which we will be able to participate to a virtual poster presentation. Instructions on how to participate to this Gather Town session will be sent soon via email to all participants. The other particular session, I would say, that we will have for the first time here in DRCN 2021 is a demo paper session, and this gave the opportunity to establish a new format for papers in DRCN, which indeed is demo papers, and it will be on Thursday 22nd, so the last day of the conference. Just few numbers about the technical program in DRCN. We had 48 submitted regular papers plus 5 demo papers, and all these papers have received at least 3 reviews, and they, as usual, went through a very selective, very tough peer review process. The peer review process has been conducted by 70 technical program committee members plus further 33 external peer reviewers. So I thank all these members, all these researchers and practitioners who dedicated their time to review and to perform high quality reviews for these papers, to keep the quality of the DRCN high as usual. So the acceptance ratio for the full papers is around 42%. Since this year we got 5 submissions for demo papers, and they were all very high quality. We decided to keep all of them, so to encourage also the evolving of this type of presentation, of these types of papers in DRCN. As usual, the diversity from the geographical point of view is very high. Also this year, we have several authors from several countries. Here there is a pie that represents this diversity for accepted papers. About topics, I've mentioned a few of them before when I talked about the topics of the 5 different technical sessions. I just want to highlight that traditional topics which usually have characterized the technical program in DRCN are still very strong, are still represented by the community, in particular, for example, topics on reliable network design and operation, or about theory and modeling, reliability of various types of networks like wireless or optical networks. But still there are new topics emerging in the submissions and also in the accepted papers, and among them I want to mention the data analytics for failure management and quantum communications and application to smart cities and verticals that we are in these years are seeing more and more. This concludes my talk. I leave now the floor to Guido, which I guess wants to say a few words also for the entire staff that participate to the organization of DRCN 2021. Guido, please, the floor is yours.
Thank you very much, Francesco. And I would like to thank all the organizing committee of DRCN 2021. I learned in these 2 years of general chairing that it's extremely important to rely on the very good and proactive team working. So I have always tried to, let's say, share any decision with the people involved in the organizing committee, and this is really the winning attitude. So I don't read all the names, but you can see all the pictures, and also on the website there is a full list. I also remind you that you can download the leaflet of the entire program together with the proceedings from the website. We sent you the links. So Francesco, if you can turn the slide. Okay, so I also would like to thank all the sponsors, starting from the technical co-sponsor, Communication Society of IEEE, the financial sponsor, CNIT, that supported us with all the registration procedures, MATED, who is a section of Polytechnico dedicated to the development of online teaching, and in particular Gianfranco Elia, as I am already mentioned him. They gave all the technical support for the webinars, registrations, and so on. This year we also involved some local chapters of IEEE Italy, in particular the Italian section Affinity Group, who managed to organize the second workshop, and the VTS chapter that basically provided some persons on the technical program committee. And finally, I would like to thank all our sponsors, companies who accepted to be patron of this conference, in particular SMA Optics, our silver patron, and the bronze patrons, ADVA, Colt, and iWay. I would like also to remind, I take the sharing for a minute, that we will have a relevant, where is it? Sorry, I don't find it. Okay. Do you see my screen now?
Yes.
Okay. So in the final workshop, on Thursday afternoon, we will have a very relevant keynote speech by Professor Nick McCune from Stanford University. I know many of the attendees knows him by his fame. He is the founder of ONF, the huge organization who is basically sharing the standardization in SDN, software for networking. And he's also the founder of Barefoot and of many other startups and companies. He will talk, he will keep his speech inside the last workshop of this conference dedicated to programmable data plane, which is a really hot topic in communications at the moment. I would like to thank the two chairs who organized the workshop, Professor Pontarelli and Professor Nurmi, were already mentioned by Francesco before. Okay, so I don't want to take more time. We are a little bit late compared to the schedule. So thank you very much, everybody. I leave the podium to the chair of the first session, technical session of the conference, Sebastian Troia.
Hi, Guido. So I'm gonna share the screen here. So I kindly ask the authors to raise their hand with Microsoft Teams. So I have one. Okay, so this is the schedule for the first session. So the first talk will be from Hong Wang from Beijing University of Post and Telecommunication. Now I'm gonna start the video recording. Okay. Can you see the screen?
Yes.
Okay, let's start.
Professors, it is a great honor to have the opportunity to give this presentation. The title of our paper is Satellite Laser Communication Assisted P-cycle Protection Against SRLG Failures in WDM Optical Networks. The presentation is organized into 5 parts. First of all, the research motivation and our works are presented. Part 2 introduces our proposed protection scheme, and Part 3 presents the ILP model. Part 4 analyzed the simulation results. Part 5 concludes the presentation and presents some future works. Optical fiber communication is the foundation of almost all network devices and applications. Protection for optical networks has always been a popular research aspect since its birth. Many protection technologies for terrestrial optical network have been studied. However, these technologies totally rely on terrestrial optical networks themselves. Thus, it is difficult to deal with large-scale link failures. Protection based on other mediums to recover affected traffic in optical fibers has also been studied, but the transmission rates in these mediums are much lower than that in optical fiber. In recent years, the performance of wireless laser links has been greatly improved and satellite laser communication has been widely studied. SLC has many advantages such as free from terrestrial disaster, large bandwidth, high data rates, and license-free spectrum. It is promising to construct a space-ground integrated optical network with global coverage, and this research has been carried on in many countries. In this paper, we applied the SLC technology in the P-cycle design against SRLG failures in CONs. We proposed a protection scheme and an integer linear programming model is provided to scheme's performance. Next, we introduced our SLC-assisted P-cycle protection scheme. First, we will introduce the concept of P-cycle protection. P-cycles are pre-configured ring-like structures formed out of the spare capacity in the network. A P-cycle can provide one protection path for every on-cycle span and two protection paths for every straddling span. In the picture A and B, we can find the P-cycle ACFGEDA can provide one path CFGEDA for link AC and two paths DACF and DEJF for the link DF. In the integrated space-ground optical network, our proposed protection scheme includes three steps. First, candidate cycles in the integrated networks are generated. Then we calculate the P-cycle protection path upon an SRLG failure, and finally we develop an ILP model for the scheme and analyze its performance. It should be noted that in the designed model, we choose satellites on GEO to provide long-term and effective protection for terrestrial services. This is the pseudo code for generating basic P-cycles. From line 5 to line 11, we calculate protection cycle for on-cycle span. When calculating the shortest path, we stipulate the priority of links in the TON. When the length of the passes one threshold value, we calculate the shortest path using satellite links. From line 12 to line 16, we calculate cycle for straddling span. The number of protection passes provided by a P-cycle for affected span in case of an SRLG failure can be 0, 1, or 2. Here we chose A, B, C, F, G, E, H, A as the P-cycle, and in case of SRLGA, we can find the link AC and BD failed, and the cycle can provide two passes for AC but 0 paths for BD because the link BD is not on the cycle. And in case of SRLGB, the cycle can provide two passes for link AC and one path for link BD, link AB. And in case of SRLG failure C, the cycle is divided into many parts, and in this time the cycle can provide one path for AC and 0 paths for CF and EF. Next, the ILP model is presented. The candidate set is calculated by the algorithm mentioned in the 2.2, and the number of the protection paths is calculated by the algorithm mentioned in 2.3. In this part, enough spare capacities are provided for working capacities, and in this part, constraints on wavelength assignment in WDM optical network are followed. Here are the simulation parameters and topologies. It should be noted that because of the recent development, each ground-to-satellite link and inter-satellite link contains 16 wavelengths, and the link in TON can contain 80 wavelengths. And both SONs in the integrated networks are composed by 3 GEO satellites, and each of which is connected with other 2 satellites and 2 optical ground stations in the TON. The cost of each united spare capacity or link is set to 1. And SRLG areas are known as priori, and each link in TON is affected by a single link failure or an SRLG failure. Here are the simulation results. For each network, 5 demand sets are used, and the number of demands in set ranges from 50 to 150 for each demand. Source node and destination nodes are generated from the node set in TON randomly, and each source destination pair only occupies 1 wavelength. Here are the results of cost, joint, working, and spare capacities. The results show that the SLC-assisted P-cycle protection needs less joint capacity than traditional P-cycle protection in TON. And here are the results of ratio of spare capacity and working capacity. The results show that the ratio of spare capacity and working capacity is smaller in SLC-assisted P-cycle protection than that in traditional P-cycle protection. Here are the results of success rate of protection. The results show that success rate of protection is smaller in SLC-assisted P-cycle protection than that in traditional P-cycle protection. Finally, we conclude the presentation and present some future works. In our paper, we proposed an SLC-assisted P-cycle protection scheme, adopted the ILP model for the P-cycle design, and analyzed the performance of the scheme in 3 aspects: joint working and spare capacity, the ratio of spare capacity and working capacity, and the success rate of protection. In the future, we will use heuristic algorithm in larger network topologies and focus on optical satellites on LEO or GEO to LEO or MEO to reduce time delay. Thank you.
Okay, so thank you, Wang Hong. Now it's time for questions. Are there any questions? Okay, maybe I can start with one question. I would like to understand how long does it take to run your proposed ILP? If you think to, for instance, in a first application, this work could be, for instance, to be applied in a SDN environment, such as the software-defined optical net. Here the time to recovery, so the time to run the algorithm is very important. So how long does it take to run all these algorithms?
Thanks for your question. We just use traditional P-cycle protection to the network.
Juan, please speak closer to the mic.
Oh, thank you. Sorry. Can you hear me?
Yes,
yeah.
Now it's better.
Thank you. Thanks for your question. And in our paper, we use traditional P-cycle protection for the network. And you said something about SDN. I just hear SDN. We didn't use that. That's my answer. Thank you.
I would have another question. The satellite links to the terrestrial nodes, do you assume that they are static or can they be dynamic? That they also can go to different nodes?
We use the satellites on JO, so it's stable, and we didn't use a satellite on LEO or MEO because it can't maintain a stable link. I don't think it is helpful for protection. Maybe in the future we will did some research on these two layers. It can reduce time delay as other advantages.
But even for geo, you can have a link to one node in one location and then a link to another node in another. So they don't need to be static.
Oh, thanks. Maybe I will think it over in the future.
Okay, good. For the future. Okay, thank you.
Thanks.
We have a question from the chat from Xin Jingjie. Can you simply explain the problem of time delay brought by GEO?
Oh yes. I have just answered we say that GEO satellite does bring some time delay, but we are studying the protection technology, so it is more important to establish a stable protection link. So we do not focus on this problem. We will think it over, and when we study recovery technology in the future. I hope my answer is helpful.
Okay. We have another 1 minute for another question. Remember, for all the attendees, if you have further questions, if you want to bring the discussion with the authors, you can write an email to the authors in order to have further discussion on papers. Okay, so thank you, Hong.
Thank you.
I ask for the second speaker to raise his hand or her hand. Second speaker, okay. Now I'm gonna start his presentation. Her presentation. Okay.
Hello everyone. I appreciate the opportunity to be with you today. My name is Wang Fei from Graduate School of Informatics, Kyoto University. Today I'm going to give a presentation on my recent research topic, load balancing model under multiple failures with workload-dependent failure probability. My presentation will follow this outline. Firstly, what is NFV and what is the benefit? In a traditional network functions are provided by specific hardware devices. Network virtualization decouples the hardware from the functions so that multiple functions can run on the same physical machine, as shown in this figure. Adopting NFV reduces the high cost of traditional network and increases the flexibility and resource utilization. Applications running in a data center generate workload in the form of computing resources, including CPU and memory. The amount of resource required for a given computing resources step is termed as workload. Higher level of workload often leads to more performance degradation. Several works investigate that the workload characteristics such as CPU utilization, memory utilization, and application type affects the failure rate. The work in PER 2009 found that CPU utilization and memory utilization are correlated positively with failure rate. The workload-related failure characteristic of each node can be different due to several reasons, such as machine probability and aging situation. Each workload-dependent failure probability reveals an empirical relationship between the workload and the failure probability. Workload can be performed by collecting and analyzing the workload-related failure characteristics of each node. The works in SCTC 2020 and GlobalCom 2020 introduced the workload failure probability, which is a non-decreasing function revealing the relationship between the workload and the failure probability. The two works address the primary and the backup resource allocation with a two-step workload-dependent failure probability to minimize the maximum expected available time with singular or multiple backup resources, respectively. The workloads are calculated based on the allocation before any failure occurs. When a function fails, one of the backup resources is activated to recover the failed function. The workload of nodes are changed against the failures. The failure probability of each node is related to each workload after variation. Thus, load balancing needs to be considered with the workload after failure and recovery. Against each failure, deciding one of the backup resources to recover the failed function after a failure requires the computation time, which leads to delay for recovery. Preventively determining priority of the backup resources to recover the failed backup resources at network operation start time minimizes the maximum available probability in worst-case failure pattern. It automatically specifies the available backup resources that has the highest priority to take over the task of the failed function, so that it does not require the computation for reallocation of the failed function after failure detection. Several various objectives of allocations in existing studies for load balancing considering the workload variation against failures. Except for focusing on the workloads and utilization ratios for load balancing, other objectives such as minimizing the execution time and max spine, maximizing the throughput and the reliability of service are taken into consideration. However, the works did not consider the workload-dependent failure probability. They also didn't consider the difference of the relationship between the workload and failure probability of the physical machines due to several reasons, such as machine property and aging situation. A question arises, is there any load balancing model with preventive recovery priority setting to minimize the maximum available probability with the workload-dependent failure probability based on the workload after recovery? Primary and backup resource allocation and recovery priority setting are determined. The problems is defined as follows. Given sets of functions and nodes, the requested load for each function, the maximum capacity for each node, the maximum number of concurrent functions failures, and the workload-dependent failure probability for each node. Our goal is to find the primary and backup resource allocation and the priority for automatic recovery, aiming to minimize the maximum available probability that a failed function cannot be recovered. Then the problems comes to how to calculate the workload and corresponding failure probabilities. When a failure occurs to function J, the backup resources in node with the highest priority is activated. The node workload under a failure pattern consists of two parts, the workload of primary source and the workload for the activated function caused by the failure pattern alpha, since node I has the highest priority among nodes in N which provide protection for function J. Given a workload-dependent failure probability, which is assumed to be a non-decreasing function, we can use an N-set function to approximate a non-decreasing function of the node workload as shown in the figure in the bottom. This is the mathematical model. The objective is to minimize the maximum available probability. Then I would like to show some numerical results to observe the basic characteristics of the proposed model. First, we consider the influence of different unsafe failure probability. The larger n is, the higher accuracy for approximating relationship between the workload and the failure probability is. With the given parameter, the n-set function is given by dividing the range of capacity and the failure probability equally into 2 and 4 sub-steps, with n equal to 4 and 8 respectively to conservatively approximate the given non-decreasing function. The maximum unavailable probability obtained by the proposed model with n equal to 4 and n equal to 8 are on average 50% and 55.5% smaller than that of n equal to 2. The proposed model with n equal to 8 is not well improved compared with n equal to 4, since the step width is much smaller than that the requested load of each function with given parameters. Secondly, we introduce 3 baselines to show the comparison on the maximum available probability between different models. Table shows the features of the proposed model and baselines. Baseline 1 is a load balancing model that minimizes the maximum utilization ratio among nodes without considering a workload-dependent failure probability. The recovery priority of each function that can be applied for all failure patterns is determined at the operation starting time. Baselines 2 and 3 considers the workload-dependent failure probability. They prepare the initial location without considering the workload variation after failure occurs. After detecting a certain failure pattern, baseline 2 activates backup resources for recovery with the given priority presented in GlobalCom 2020. Baseline 3 recalculates the reallocation solutions at the operation runtime considering the workload variation after failure detection. Comparing proposed model and the traditional load balancing model without workload-dependent failure probability, the maximum unavailable probability in the proposed model with n equal to 4 is in average 1.5 times smaller than that of baseline 1 among different maximum number of failures. The workload after activation of backup resources of field function is divided evenly for each node. The workloads obtained by the proposed model are adapted to the workload-dependent failure probabilities so that the maximum available probability is minimized in the proposed model. Comparing proposed model and workload-dependent models without workload variation after failures, the maximum available probability obtained by the proposed model with n equal to 4 is in average 45% and 8.3% smaller than those of baselines 2 and 3. The computation for baseline 2 is not required since the priority is given in advance. The computation of baseline 3 is in average 145.5 seconds among all cases. This is the conclusion of today's presentation. We proposed a load balancing model to minimize the maximum available probability with the workload-dependent failure probability based on the workload after recovery. With the workload-dependent failure probability, a service provider is able to provide each service by minimizing the unavailability among functions. For protection of each function with multiple backup resources, we introduced a recovery strategy which can be applied for each failure pattern. The recoveries are automatically operated according to the priority after failure detection. The numerical results observe that the maximum available probability in the proposed model is suppressed as an increase. The proposed model reduced the maximum available probability compared to the baselines. That is all for my presentation. Thank you for listening.
Thank you, Zhu Mengfei. Now it's time for questions. I can. It's not a question. It's just a curiosity. I think it's very nice work, and I would like to know what are the next steps of this work.
Okay, thank you for your comments. Can you hear from the mic?
Yeah,
Yes.
we can hear you. Yeah.
Okay, thank you. About the thanks for your comments. The next step of this work is to provide a heuristic algorithm to solve this problem. Since as is in the numerical results part, we are really doing a small size network for the evaluations. So especially for the n-set function to approximate a non-decreasing relationship of the workload and the failure probability, it do need a lot of computation time. So our next step is to provide a heuristic algorithm to solve this difficulty. Thank you.
Thank you. Other questions from the audience? The chat. Okay, so if there are no other questions, I will move to the third presentation of today. I asked to Mitsuki Ito to rise the end. Okay. So thank you, Drew Menfei.
Thank you.
So now I'm gonna share the presentation here. Okay.
Hello everyone, I'm Mitsuki, a graduate school student of Kyoto University in Japan. Today, I'd like to talk to you about the backup model of cloud providers, which determines both primary and backup allocations of virtual machines under uncertain capacity demands. Here is the outline of my presentation. First, I'll describe the background of our work and move to conventional models. After that, I'll introduce our proposed model and show results of numerical evaluation. Finally, I'll conclude my presentation. Okay, I'd like to start by talking about the background. Cloud computing provides configurable computing resources such as servers, storage, networks, applications, and services to users through the internet. For infrastructure as a service, users can use infrastructure resources such as CPU and memory, represented by virtual machines. When users request some resources, the cloud provider allocates a proper number and proper types of VMs stored in physical machines. The availability of VMs in cloud providers is increasingly important. When failures of VMs occur, they lead to huge financial damage to both cloud providers and users. Pre-planned backup VMs enable the cloud providers to enhance the availability, since the backup VMs take the workload from primary VMs when any failure occurs. The backup capacity is reserved for the corresponding VMs. In case of failures, only the VMs in the failed primary VMs are switched over to the predetermined backup VMs. There are some protection approaches. First, I introduce the dedicated protection, which is a straightforward approach. In this approach, the backup capacity is prepared just as a mirror of the allocation in primary VMs. Therefore, every random failure scenario is absolutely protected if the backup VM is active. However, since twice the amount of the capacity in primary VMs is required in total, this approach is very inefficient. In order to use the backup capacity efficiently, the probabilistic protection is applied instead of the dedicated protection. In this approach, the probability that the protection fails due to insufficient backup capacity does not exceed the survivability parameter epsilon. If we use this approach, Failure of the protection can happen with the probability of epsilon, but the total backup capacity is reduced by sharing the backup capacity among VMs in primary PMs, compared with the dedicated protection. In this slide, I introduce the overview of backup problem in a cloud provider. We assume that primary PMs have a failure probability and any backup PM does not fail. The objective is to minimize the total backup capacity. We determine the allocation of each VM, and accordingly, the backup capacity of each backup PM is computed under the constraints such as probabilistic protection guarantee. We introduce two conventional models. The first model to determine the backup allocation is formulated as shown in this slide. The total backup capacity used in all backup PMs is minimized under the constraints such as probabilistic protection. The constraint of the probabilistic protection means that for each backup PMK, the probability that total demand of failed VMs exceeds the backup capacity is less than the survivability parameter epsilon. Note that this model calls for the exactly determined capacity for each VM. Actual clouds allow VMs to scale up and down dynamically as demands change. There are several approaches for the scaling. Horizontal scaling offers scaling by adding more VMs or removing over-provisioned VMs. Vertical scaling provides scaling by changing the size or the capacity of VMs. The second conventional model considered vertical scaling in addition to the first conventional model. The second conventional model can determine the backup allocation of VMs without directly handling the dynamic change of VMs. Robust optimization is applied. Considering the conventional models, a problem arises. The conventional model only determines the backup allocation. The allocation of VMs in primary PMs is given in advance. However, cloud providers receive demands from users and need to allocate them to primary PMs while determining the backup capacity allocation. In addition, as with the second conventional model, it is also required to be robust against the uncertainty of VM capacities. Therefore, our challenge is to formulate a model which determines both primary and backup allocations under uncertain capacity demands. Given a set of requests, the proposed model can determine both primary and backup allocations, which satisfy the probabilistic protection guarantee. The proposed model can deal with the uncertain VM capacities by introducing an uncertainty set. The parameters and variables used in our model is shown in this slide. The proposed model considers several request types, such as small, medium, and large. The requests given in the proposed model belong to one of the request types. We explain the uncertainty set in this slide. The uncertainty set is a set of constraints concerned with the uncertain parameters. It is required to solve optimization problems in which some uncertain parameters are used. In the proposed model, the constraints of capacity demands in the uncertainty set G are expressed as follows. The first equation indicates that for each request type, the total capacity demand is not greater than CRR. The second one shows that the total demand of all request types is not greater than CR. The third one restricts the upper and lower bounds for each capacity demand by gamma R and delta R, respectively. The optimization model for both primary and backup allocations under uncertain VM capacities is as follows. As with the conventional models, the objective is to minimize the total backup capacity. Binary variable WIRK denotes the allocation of demands to primary PMs. Similarly, binary variable XIJRK denotes the allocation of demand to both primary and backup PMs. The capacity demand of each request, DRK, is an uncertain parameter, and it is constrained by the uncertainty set of Z. We consider the demand uncertainty in both primary and backup PMs. With the robust optimization technique, the probabilistic protection constraints are transformed by using gamma J, which is the required number of primary PMs protected by backup PMJ to satisfy the probabilistic protection guarantee. When computing the total backup capacity, gamma J primary PMs, which are protected by backup PMJ and have the largest capacities, are considered, which means that the largest capacity under the probabilistic protection guarantee is used to compute the backup capacity. In addition, the maximum capacity under the uncertainty set of G is considered to be robust against the uncertainty of VM capacities. Let me move on to numerical evaluation. The setting is as follows. We consider 4 primary PMs and 4 backup PMs. The capacity of each PM, including primary and backup ones, is set to 1,500 MIPS. We assume that a set of request types, such as small, medium, and large, and requests belonging to each request type are given. The setting concerned with the request are shown in the table. As an evaluation metric, we use the total backup capacity, which is the objective of the proposed model. We compare the proposed model with the second conventional model, which considers uncertain VM capacities. Since the conventional model cannot determine the primary allocation of demands, we introduce 2 policies for the primary allocation. The objective of the bin packing policy is to minimize the number of primary PMs used to allocate the demands. The objective of the load balancing policy is to minimize the maximum workload among primary PMs. For the conventional model, the primary allocation is determined by either BP or LB policy. After that, the required backup capacity under the obtained primary allocation is computed. We evaluate the total backup capacity by changing the failure probability P and the survivability parameter epsilon. Epsilon is set to 0.0001 when changing P, and P is set to 0.01 when changing epsilon. The numerical results show that the proposed model can reduce the total backup capacity compared with the conventional model with each policy. This indicates that the proposed model offers an optimal allocation of demands to primary PMs when considering the backup of those demands. Next, we consider another evaluation. Based on gamma R, delta R, and CRR are determined by using given parameters. We set delta R as rho gamma R, where rho is a given parameter. We set CRR as mu kr gamma R, where mu is a given parameter. Then we evaluate the total backup capacities with different values of rho and mu. When mu is less than 1, as mu increases, the total backup capacity becomes large for any rho. In addition, for fixed mu, the total backup capacity for rho equals 0.4 is larger than or equivalent to that for rho equals 0.6, and the same relationship appears between rho equals 0.6 and 0.8. This is because the larger rho becomes, the more the range of the capacity demand uncertainty decreases, which leads to reducing the overestimated capacity. On the other hand, when mu is larger than or equal to 1, the total backup capacity is constant and common for all values of rho. This is the conclusion. Our problem is that the conventional models only determine the backup allocation. The allocation in primary PMs is given. Cloud providers receive demands from users and need to allocate them to primary PMs while determining the backup capacity allocation. It is also required to be robust against the uncertainty of VM capacities. Then we formulated a model which determines both primary and backup allocations under uncertain capacity demands. The proposed model can deal with the uncertain VM capacities by introducing an uncertainty set. From the numerical evaluation, we find that the proposed model can reduce the total backup capacity compared with the conventional model with each primary allocation policy. Thank you for listening.
Thank you, Mitsuki Ito. Now it's time for questions. Okay, I have a curiosity. I was wondering, are you planning for the next step of this work to apply here machine learning, such as I was thinking it could be nice to see if you could predict what can be the primary and backup allocation. If yes, how you could apply this in your work?
Okay, thank you for your question. So your question is, are there any extensions for the model with machine learning or something?
Yeah.
Okay. At this moment, the application of machine learning is not considered, but some heuristic approaches are considered in the future, as with the Schumacher in the previous presentation. Is it okay?
Okay. Are there other questions from the attendees?
Hi, can you hear me?
Yes.
Thank you for your presentation. So I do have one question, but since I'm not an expert, it might sound not proper or something. So in the figures, like you showed that the backup link, I guess, that it was the measurements, like there was not much of an improvement in the reduction. So I wonder if there's a soft limitation on how much reduction you can achieve, or is there anything else?
Okay, thank you. So your question is that how was the reduction of the proposed model compared with the other conventional models?
Yes.
Okay. So as the figure shows, for some parameters, the difference was 0. So the total required backup capacity is same as each other. But some parameters for some parameters, the proposed model can reduce the capacity. So I think since the size of the problem is small, the difference is small. But if we consider the more larger size problem, the difference becomes large, I think.
Thank you.
Okay, thank you.
Other questions? Okay, we can move to the last presentation of this session. If you have questions for the authors and you won't have further discussion, please don't hesitate to write them an email. Let's move to the last presentation will be done by Yacheng Zhang from the University of Nottingham, Ningbo, China.
Good morning, ladies and gentlemen. It is my pleasure today to make a presentation about our paper, WLHCK Weighted K-means-based LHC algorithm for cluster head selection. I'm the second writer of the paper. My name is Yacheng Zhang, and our group is from the University of Nottingham, Ningbo, China, and our tutor is Pushpendra Kar. In today's presentation, I will mainly focus on 4 parts. In the introduction part, I will give you a short introduction to our protocol, WDCK, and its background, Wireless Sensor Network, WSN, and in the second part, I will explain to you how our protocol, WDCK, works under the background of Wireless Sensor Network. And for the result analysis part, I will show you the comparison of our protocol with two existing protocols and show you the advantages of our protocol. As for the final part, I will talk about the originality and limitations of our paper and our protocol, WDCK. So let's now move on to the first part. In general, the topic of our paper is to study the issue of energy consumption of WSN, and our main focus is to reduce the energy consumption and extend the lifespan of the network. So what is WSN? WSN has its full name, Wireless Sensor Network. It is a big data collection network with limited energy. And as you can see from the picture, it shows you the basic structure of WSN. From the picture, we can see that it has three main components. They are sensor node, which includes the non-cluster head and a cluster heads, a sync node, and a base station. So how does WSN works? In general, it has two processes. The first one is called the setup period. It includes two crucial steps, cluster division and the cluster head selection. And the second process is a stable period. In this period, data transmission occurs. So why does the first process, the setup period, is so important? Because cluster division and the cluster head selection directly influence the second period. This means that if we can optimize the cluster division and the cluster head selection, we can greatly reduce the energy consumption in data transmission part, and in this way, we can greatly prolong the lifetime of WSN. And there are two main directions of current works that try to improve this issue. The first one is to design some protocols on clusters division, and the second one is to modify the routing path selection process. And there are some existing protocols. I think among them, the most famous one is LEACH. That is a low-energy adaptive clustering hierarchy, and it has a centralized version, LEACH-C protocol. As for the clustering algorithm, I think K-means is widely applied. In general, our protocol, WDCK, is based on the centralized version of LEACH combined K-means algorithm, and we make some modification to the cluster head selection part. And in this part, I will explain to you in detail how our protocol works. As you can see in the flow chart, it shows you the logic of our protocol in the setup period. In the first step, each sensor node will sense its location and the residual energy to the base station, and the base station will calculate the number of optimal cluster head, and then divide clusters by K-means algorithm. This two step is how the clusters division step works. And then we come to the next crucial step, cluster head selection. Under our protocol, only the sensor node whose residual energy is above the average level can become candidate for the cluster head and can enter the list of potential cluster head. And when deciding whether this sensor node can shoulder the responsibility of a cluster head, we use the determinant TI value here. It is the multiple of total intercluster distance times and the residual energy. Under our protocol, only the sensor node whose TI value is the smallest can become the cluster head in this cluster. So after all the clusters are divided and all the cluster heads are selected, The base station will wide broadcast the result of clusters and the list of cluster head to each sensor node. And then we move on to the stable period. In the stable period, in each cluster, the normal sensor node will first transmit data to the cluster head, and then, after data fusion and data integration, the cluster head will then transmit the data to the sync node, and then to the base station. And this is how the protocol works. I want to clarify three things here. The first one is our protocol is a centralized protocol. This means that all the calculation step is done in the base station, and we can reduce much energy involved in calculation at each sensor node level. So under our protocol, each sensor node may have longer lifespan because it will not lose much energy in the calculation step. And for the clustering step, we compare the weight of distance and the residual energy in cluster head selection. And for the determinant of the cluster head in each cluster, we use our determinant Ti here. As for the result part, we compare our protocol WLHCK with two existing protocols, LICH and LICH-CK protocol. LICH-CK protocol is the LICH-C protocol combined k-means. And these two pictures shows you the comparison of lifetime of different protocols and the total energy consumption for the first 100 nodes for the 100 runs. As you can see in the picture, our protocol can effectively prolong the time of the first node die, and it is very effective in extending the stable period. I want to clarify one thing here. The stable period here means the period that the total 100 node stays alive in our period. In other words, in the stable period here, no one simple node dies. In this way, we can ensure the completeness and accuracy of the information collected. And these two pictures shows you the comparison of the number of alive nodes and the comparison of the network residual energy. As you can see from the picture, the energy consumption of LICH-C is much more and much rapid than both the LICH-CK and the WLHCK algorithm. For the originality of our paper, I think our protocol WLHCK can prolong the time before the first node die occurs in the network, and thus increase the stable period of WSN. It is very useful in systems where each sensor node is of equal importance. This means that we cannot endurance the death of even one sensor node. We require each sensor node have very long lifespan in the system. However, as for the limitations of our paper, we just assume that each sensor node can transmit information to the cluster head through one single hop. This means that we do not take into consideration of multi-hop cases. Maybe some further investment and investigations and some researches can be done for the multi-hop cases. That's all about our paper and our protocol. Thanks.
Thank you, Chen Zhang. Now, yes, time for questions. I can start with one question. So I didn't get how you calculate in your methodology, how you calculate the optimal number of cluster heads at the beginning. Maybe I missed this part.
Actually, in our protocol, we calculate the number of cluster head by writing a MATLAB algorithm. Maybe the most part of it is about how the MATLAB algorithm works. So I do not mention too much about this part. And as for our protocol, we choose 100 nodes. So if we put the number of nodes into our protocol, the answer will give out. Yeah.
Since K-means is very sensible to the number of cluster heads, so did you try to change this number just to see how it would change the results? Or you will do that, or you have done that already?
We started this issue first by using the mathematical way and deduce the optimal number of cluster head, and then doing the MATLAB simulation.
Okay.
I have a question. So, how is your protocol can be combined with like current 5G or 4G or even Wi-Fi network? Does it have to be a standalone protocol, or it can be combined with existing networks?
Well, I think our network will have much more practical importance in something like the firework warming, because we mentioned in our paper that each sensor node is of equal importance. This means that all the nodes are very important. So maybe our protocol can be very useful for the forest firework monitoring. Because maybe even one very small area in the big forest can be very important, and we cannot let it be at the risk of fires. And as for the 5G or Internet things, actually maybe we will do further investigations to study whether it can have some applications.
Thank you very much.
We have time for one question still. Okay, so if there are no other questions, so we have this the first session of the conference is done. So we are in time, Guido, even if we were late at the beginning.
Thank you very much to all the speakers and especially to Sebastian. So now we have the lunch break, and at 1:30 local time, we will have the beginning of the first keynote of the conference given by Professor Jafar El-Milghani. So I just would like to wish you a nice lunch, and I am therefore sharing today another food, typical Italian food, this time local from Milano, risotto alla milanese. So thank you very much, and see you at 1:30.